Good afternoon, judges. We're Team 1, and we're here to solve one of the biggest paradoxes in finance. You can't manage what you can't measure. The objective of this codon is to develop a reliable and defensive model for predicting Scope 1 and Scope 2 GHG emissions for firms that don't report them directly. And let's be honest, trying to model a global company's environmental impact using a spreadsheet is like trying to model the global economy using linear regression. It's a good start, but you are going to get roasted. We immediately identified the core challenge, the massive black hole of missing ESG data. Our goal is not just to make a prediction, but to design a pipeline that can produce accurate, stable, and explainable predictions at scale. Our insight, emission behavior is nonlinear. Therefore, our final approach combined rigorous data cleaning, adding external data, and a strong nonlinear XGB boost model. Our first task was performing an EDA, in which we found a few problems, but as problem solvers, we fixed these like light work. Our biggest problem was extreme right skew data, so we applied no log 1p to reduce skew.
Looking closer into the data scaling issue, we identified during our EDA process, this was the data before the scaling, and we can see how right skewed the revenue Scope 1 and Scope 2 data are. To address these problems, we implemented a structured cleaning pipeline. We applied NP log 1p function to revenue and emissions to reduce right skew and stabilize learning. For missing ESG fields, we use median imputation to maintain consistency without introducing bias. To reduce sparsity, we applied a variance threshold to drop low information categorical features, improving both speed and clarity of the signal. And for external data, we normalize formatting and aggregating everything at the entity ID level, ensuring clean one-on-one alignment across all sources. With the structural issues resolved, these post-scaling histograms reveal that scaled revenue and emissions value, along with reporting gaps, were still distorting feature scales, reinforcing the need for further transformation. After resolving data issues, we tested several models. Linear models consistently underfit because they couldn't capture nonlinear interactions between features like revenue, sector, and region. XGBoost performance performed best. It picked up the complex relationships while remaining stable across all data pools.
When it comes to the model, XGBoost model, we built two of them for Scope 1 and Scope 2. The N estimators is the maximum number of trees a model can build. The early stopping rounds, what it does is if the model does not notice any improvements at 50 rounds, it stops. The learning rate of 0.3 helps hold the model for better accuracy. The depth of 8 is strong enough to capture nonlinear patterns, and I'm telling the model to look at 90% of the data and patterns each time. This helps generalize better and avoid overfitting. The error metric the model uses is to minimize the RMSE values. Cross-validation. The function CV-RMSE runs a 5-fold cross-validation test. This prevents the model from just memorizing the data. Basically, instead of training the model, we split the data into 5 parts, 4 training and 1 for validation. We make a fresh copy of the model, we train it on the training part, then we predict on the validation part. And we calculate the RMSE scores, which tells us how far off the predictions are. At the end, the function returns the average RMSE values across all 5 splits. Utilizing the function, what I do next is run the cross-validation function on both of my models. First, I run it on Scope 1, which gives me an average RMSE value of 1.94, and then I run it on Scope 2, which gives me an average RMSE score of 2.43. These values are in log space, so they basically tell us that the model can get the emissions within the right order of magnitude, which is the main goal of this kind of prediction.
So, we have shown you the technical rigor, but what makes our model different is its reliability. Thanks to log transformation and XGBoost, our model is highly capable, highly stable across all folds, which is absolutely critical for emissions data. This translates directly to business impact for Fitch. Our solution fills those missing emissions gaps, producing estimates that are guaranteed non-negative and reliable. That's why our model is the best foundation for Fitch's sustainable future. You can trust this data in your models, you can trust these numbers to your clients, and you can build a stable product on top of it. That is why our model is the best foundation for Fitch's sustainable future. And lastly, we are UIC freshmen Isabella Wu,
Nishita Srigadi,
and Vinutha Depala.
Remember our names when you choose the winners. Thank you.
Thank you.